This is the second part of our series about astrolabes. In the first part, we introduced the astrolabe and showed how to tell the time during the day. There are many other calculations that can be performed. Indeed, in the 10th century, Abd al-Rahman al-Sufi described 1,000 different uses of an astrolabe in astronomy, astrology, navigation, surveying and timekeeping. In this short video, I'll just cover a couple of simple calculations. Last time we saw how measuring how high the sun was in the sky allowed us to estimate the time of day. At night time the sun is below the horizon, of course, but we can still use a star. For example, suppose it is early in the morning of April the 14th and the star Arcturus is in the west. We've used the astrolabe to measure that it is 40 degrees above the horizon. What time is it? We're rotating the reed so that Arcturus is on the 40-degree line, and remembering that the 14th of April is 25 degrees in Aries, we can align the pointer and see that the time is 4 o'clock in the morning. One way to measure the azimuth of the sun is to align the pointer and read off the angles. Apart from the risk of staring directly at the sun, it is also quite hard to be accurate. If, however, we have a post stuck vertically in the ground, we can use the length of its shadow to give us the angle. Suppose the post is 7 feet tall, then the 7 shadow square in the lower left quadrant on the back gives us everything we need. If the shadow is, for example, 8 feet long, then the sun is 41 degrees above the horizon. Astrolabes can also be used for surveying. Let's measure the distance to a remote object as an example. First, we measure the angle from some arbitrary point to the object of interest. In this case, the object is 8.5 degrees from the east. Now the astrolabe is moved directly towards the arbitrary point, let's say by 10 meters. The new angle is measured, and in this case it is 2.5 degrees from the east, so the difference in angle is 6 degrees. The lines on the top left quadrant are a sine table, so if we set the angle to 6 degrees, then the pointer crosses the outer arc at this point, which is just over 5 lines up. Let's say 5.2 out of the possible 50 lines. This means that if the remote point was 50 meters away, the angle would represent 5.2 meters along the ground. But we actually moved 10 meters, so the remote point is 50 times 10 divided by 5.2. That is about 96 meters away. Obviously, knowing the distance and measuring the angle of inclination would allow us to similarly calculate the height of the remote object as well. The moon's cycle varies over the course of a year, and a table of positions is required in order to be completely accurate. In the next video, we'll cover where to get such a table and how to use it. But a rough approximation of the moon's movements can be obtained using just the engravings on the back of this astrolabe. Suppose we want to know what the date of the new moon is in May 2018. The first step is to work out the golden number of the year. This can be calculated by dividing the year by 19, taking the remainder and adding 1. So 2018 has a golden number of 5. Locating the golden number on the back of the astrolabe shows that the first full moon after the spring equinox falls on approximately March the 31st. That is 11 degrees after the equinox. The moon symbol here shows that over the course of a lunar month the sun moves 29.5 degrees. So, to get to the May new moon, we have to multiply that by 1.5. 1 to get to the next full moon, which is in April, and 1/2 to get to the new moon in between the full moons. This gives us a total of 55 degrees after the equinox, or 25 degrees in Taurus, which is May the 15th. The actual new moon was at 12:57 on the 15th, so on this occasion the prediction of the moon phase is pretty accurate. So there's a few example calculations that you can perform using the astrolabe. This has been the second part of our series about astrolabes, and I've been using a custom astrolabe from the Rose Keep Etsy shop.